Hey guys, welcome to part 11 of the Magnetism series. This is the second half of our look at the Biot-Savart law. Now in this video, we're going to be solving for a special case using the Biot-Savart law. And this is when we have a point at some distance, let's say some distance x, away from an infinitely long straight current carrying wire. Lots of adjectives there. But when we think of infinitely long, one way that you could put this into perspective is you could say that the distance x from the wire to the location at point P, that distance is much, much smaller than the total distance, or the total length of the wire, should I say. So that's one way that you can think of it. Now we're going to be using the Biot-Savart law and then learning how to manipulate it using calculus to solve for the magnetic field. So let's get into it. Alright, so what we see here is point P, and that's a point where we're trying to figure out the value of the magnetic field. Now, we break up our wire, remember, into little current elements, dl. Now, in this equation, the way that I've written out the Biot-Savart law is using dy instead of dl, and that's just because I'm working up and down here along a y dimension. Now I've also labeled r as the distance from dl to point P, and x is the distance from point P to the wire. And then, of course, the value of y is the distance between this point, between x and the point P, and dl and that point. So what I'm going to do here is take the Biot-Savart law, which remember is mu naught, the vacuum permeability over 4 pi, that's constant, times I, which is the constant current in this wire, times the integral of dy sine theta, or integral cross r hat, integral dy cross r hat over r squared. Now what are the things that are going to be changing? Well, r is changing as we work our way up here. And then of course y is changing because we're focusing on a different current element, dy. But x is staying the same. So what we want to do is we want to get as many constant things in here. Right now we've got things in terms of y, things in terms of theta, things in terms of r, and that's a whole lot to be working with. So let's do this first. So we've got this expression r squared is equal to x squared plus y squared just from the Pythagorean theorem, but it's allowed us to write r squared now in terms of x squared, which is x being constant, and y squared. So now at least we've got a y here and we've got a y here. So the next thing we can do is write theta, or sine of theta, in terms of y. So that would be easiest. So if we're going to use this constant x again and y, we could say the tangent of this angle is negative x over y. So now that we have tangent theta equals negative x over y, we can see that we've now got a y value here that can relate to dy, and we can solve for y, and we can take the derivative of it, which can then substitute for dy. So if we solve for y, we get y equals negative x over tangent theta, and then if I take the derivative on both sides, I get dy is equal to x d theta over sine theta squared. And then if I write out what sine of theta is, which is x over r, I have x d theta over x over r squared, which when simplified is r squared d theta over x. So now I can take this expression over here and I can substitute it in for dy right over here. And the whole point of doing this was to get rid of certain things, right? We wanted to be able to get rid of having too many different changing variables. And you can see now once I've substituted this in, I'm going to be able to make some simplifications. So once I substitute in r squared d theta over x for dy, what I will end up with is r squared d theta sine theta, so r squared d theta sine theta over r squared x. And then you can see that x is constant, so it will end up coming out front here, and then our r squareds will cancel, and so I'll be left with the expression mu naught over 4 pi x times the integral sine theta d theta. Now the limits of integration here, we're going to integrate from 0 to pi, right, as we work our way up the wire. Okay, so now I'm going to do the integration, and when I integrate sine theta d theta, I get negative mu naught I over 4 pi x times cosine theta from 0 to pi. And then if I evaluate it from 0 to pi, cosine at pi is -1, and the minus the cosine at 0 is 1. And because I have that minus sign in there and the negative out front here, it ends up being 1 plus 1, which is just 2. So I have mu naught I times 2 over 4 pi x, and that simplifies down to mu naught I over 2 pi r, or mu naught over 2 pi times I over r. So this is a lot of calculus for sure, and it can be intimidating to some people when they're first taking a calculus-based physics class. So watch it a few times and try to look for the patterns, because you'll see them a lot across many different areas of physics. But above all, remember the most important thing. The Biot-Savart law is really just looking at the relationship between the current running through a wire and the magnetic field that can be detected or measured at some position r away from the wire. So it's really just trying to relate that idea. We know there's magnetic field around the wire. How strong is it? And this equation tells us. This specifically, this simplified version, is only for a long straight wire with a constant current. But this equation is actually oftentimes used to approximate the magnetic field around a current carrying wire in most cases. But since you are in a calculus-based class, you're able to take the first function, the Biot-Savart law that we had before, the mu naught over 4 pi, and so on, and really adapt that to multiple situations. So you can take a situation where maybe you have a loop of wire with a current running through it, or a curve of wire, or any kind of shape like that, and then just work out, like we did here, how to adapt that to the situation in question. And you'll come out with a function for the magnetic field strength at a particular point, or at any point around that current carrying wire. So in the next few videos, we're going to take a look at solenoids and how the magnetic field works in those, as well as toroids. And we will also look at Ampere's law and see that it can sometimes be a lot simpler version of this law, as long as we have some symmetry. See you soon.